Okay, geometry, we're moving on into chapter 2 now, where we're kind of getting away from lines and segments and focusing more on angles. However, before we do that, we kind of have to go back to lines and segments for a minute. We need to define something new here called a ray. An array is a set of collinear points, very much like a line, extending forever in just one direction from something called an endpoint. So a ray is kind of a combination of a line and a line segment. We actually start from the endpoint, which is a little bit ironic. So we'd come up with one point right here and maybe just call that point A. And now we simply draw a straight, I don't want to say line or line segment right here, but a whole bunch of points that extend forever in just one direction. That's what a ray looks like. Now, what's going on here? If we're going to name a ray, we name it starting with its endpoint here, which is A, but then we need to name it with one other point that's located on the ray. So if I were to name a point right here and call that B, we could call this ray AB. And the symbol for a ray is, shocking, a ray. There you go. And so we can read that to say that this ray starts at point A, that's your endpoint, and extends forever through point B. However, there's an infinite number of points on that ray, so if I named a second one over here and called that C, we could call the same ray here by the name AC. It still begins at point A, that's still our endpoint, but it extends forever through point C as well as through point B. So these are two equivalent ways of naming the same ray, and just for fun, let's put a third one right here. If I put a D out there, the same ray still begins at A, but passes forever through point D. So these are three equivalent ways of all naming the same ray. But a little note right over here, guys, this is important. Ray names are not reversible. So with the ray that we have drawn here above, you could not simply take the name AB and reverse that and make it ray BA. You can do that with lines, and you can do that with line segments. That's the easiest way to come up with a new name, but it does not work with rays. Why not? Because ray BA starts at point B and extends forever through point A. So what I just drew there in yellow would be ray BA. That is not the same as ray AB that we had there just a second ago. So let's be aware of that. So you can't name it BA. Another common thing that people do wrong, you can't take the same blue ray that we had above and call it, for example, ray BC. Because again, BC means something different. Ray BC has an endpoint at point B. So ray BC would begin here and extend forever to the right through point C. So what I have there in yellow is what ray BC looks like, and that's not the same as the original blue ray that we named 3 times up above. So just be careful here. There are an infinite number of ways to name a ray, but it's important that we understand the first letter always has to be the endpoint, which for this ray is A. Okay, so now that we've talked about what a ray is, quick thing to add to that right here, opposite rays now. 2 rays with a common endpoint extending in opposite directions. So let me just start by drawing one ray here, and I'll call that point P. And if I draw a ray coming out of point P, it can go any direction we want it to go. So I'm just going to extend this one kind of down and to the right, and I'll call that point Q. Okay, so there's ray PQ. What we're now going to do is draw a second ray, but it's going to have the same endpoint as ray PQ. So that's got to be point P. So my second ray is going to begin from the same point P, but go not just in a different direction, but completely in the opposite direction. So it's going to extend out in this direction right here, and I will call that point O right there, trying to get my alphabet in order right there. So we've got 3 points right here, O, P, and Q, and I really want you to look at that as 2 rays here. A green ray, that would be PO off on the left right here, so this would be ray PO, and then a blue ray over here on the right, which would be ray PQ. Now those 2 rays, they have a common endpoint, and they extend in completely opposite directions. But of course you'll notice, as I'm sure some of you guys have as well, that if I were to just change the color maybe of everything that we have right here, and if I were to make all of that black, let's say, this doesn't really look like 2 different rays anymore. What it looks like is a line that goes maybe from O to Q. Okay, and really, that's exactly what's going on right here, guys. When you have two opposite rays, you basically are forming a straight line. And of course, we never need to say straight, we're forming a line right there. So that's what opposite rays look like, and that phrase will come in handy with some definitions we're going to get to a little bit later on in this section. Okay, now that we've talked about what a ray is, now we're getting into the real heart of section 2.1. What is an angle? Something we're going to talk about a lot during the course of the year here in geometry. And our formal definition is pretty simple. An angle is formed when you have two rays with a common endpoint. That's really it. So, similar to what I just did when I drew opposite rays, I'm going to start with a point and a ray extending out of that. And let's see, I'm going to go with, put a J right over there, and we'll throw a K right there. Okay, so we've got ray JK. And now I'm going to draw another ray with the same endpoint, but not going in the same direction, not going in the opposite direction either, just going in a different direction. So I'll draw another ray now coming out of point J, and I will call that one point I. There you go. So we have two rays, JK and JI. Because they both start at point J, that tells us that they have the common endpoint that we needed. Guys, this is what an angle looks like. It's made up of two rays, which means it extends forever in these two directions right here. But what isn't going to change, no matter how far we extend those rays, is how wide open this angle is right here. So what I just drew in red there is what we kind of call a circular tick mark, or an arc mark, I think is kind of fun to say. And that's what an angle looks like. So again, no matter how far we extend this ray here or this ray out here, this angle, I'll make a double out of that arc mark there, is always going to stay the same size. And we'll talk in just a minute on the next slide, actually, about how we measure the size of an angle. Okay, couple words we better get down here, a little vocabulary. The vertex of an angle, guys, is the point where the two rays come together. So in this particular angle right here, the vertex is point J. So I don't think we need to formally define that, but if you did this diagram carefully in your notes, I think you would have it. The vertex is where the two sides meet. Now, I just said the word sides. That was the next one that I wanted to define right there. So the sides, can I do this right here? Sure, we'll go copy and then we'll paste it down here. The sides of the rays, of the angle, are the two rays that we're talking about. Our sides here would be ray JI and ray JK. Now, the interior and the exterior of an angle. Every angle is going to divide the plane that it's cut up into two parts. The interior, I think we know what that word means, guys, is the inside of the angle. And the exterior, then, is going to be the outside, everything else. So if I did some highlighting right here, this might get a little bit messy, but the interior is going to be, all right, everything right here in this particular region here. It's a big region that goes on forever, because remember, that extends all the time. And exterior then, this is going to get messy, is going to be everything else out here. So you really can't shade everything here in the exterior because that goes on forever then too. So every point that you could draw then is either going to be in the interior of your angle or on the exterior of your angle. Okay, so that's some vocab right there for how an angle works. Now let's talk about naming an angle. This is something that was important in Chapter 1 when we were learning how to name points, lines, planes, line segments. Naming an angle is important too. There's really 3 different methods for naming an angle. We need to know all of them, and one of them actually has 2 variations. So we're going to write down 4. The most common way of naming an angle, first of all, we use this abbreviation right here, or this symbol for angle, and the most common way of naming an angle is with 3 points, one of which is located on each of the 2 rays, and the middle point has to be your vertex. So I could name this ray starting right up here at point I, then hitting point J in the middle, and then going back to point K. So I could call this angle IJK, and that would be a name for that particular angle. You can also completely reverse that and go in the other order. Start at point K, hit J in the middle, and then end with point I. So we could also call this angle KJI. I. That's probably the best and most specific and most thorough way of naming an angle. However, there's a couple shortcuts we take as well. If the diagram is relatively simple, you can get away naming an angle just by its vertex, which in this case here was point J. Now I'll show you in a minute when you can't do that, but in this example, because there's only one angle here drawn, you can call that simply angle J. The fourth way is maybe the easiest when it applies right here. Once in a while, they'll put a random number. Usually they'll start with 1 and then go up from there, but it really could be any number. They'll draw a number inside an angle right near its vertex, and if they do that, you can simply call this angle and then just name it by the number. This would be angle 3. So there's 4 different ways of naming that angle there. Real quick, I said I would come back and talk about why this doesn't always work. You are going to see diagrams here, actually, before too long, where you've got something that looks like this. Here's a ray, here's another ray, and here's a third ray coming out of the same endpoint. And the issue here would be that if I were to name these points here, I'll just call this A and B and point C, and we'll call this one over here point V for vertex. The problem with naming an angle just by its vertex, it works fine in a diagram like this one up here when there's only one angle that has its vertex at J. But with this diagram I drew in black here just a second ago, if I were to ask you guys which angle is angle V, V being our vertex, I might be talking about this angle right here, angle AVB. Or I might be talking about this angle here, angle BVC, or there's a third one here, I could be talking about angle AVC. So there's actually 3 different angles here in this diagram in black, and they all have their vertex at point V. So in that situation right there, you would not want to just name your angle by its vertex because there's some confusion right there. You can't tell which angle it is that we're talking about. So in a simple diagram like this with just one angle, yeah, go ahead and use that one-letter vertex method. But in a more complicated diagram like this, you don't want to use that, and you're going to want to use 3 letters. Okay, the next thing I wanted to discuss, not hugely important here, guys, to be honest. It's called the protractor postulate. That phrase comes from our old textbook. I don't even think that our new one uses it, but real quickly, it just says the following. Every angle can be measured using a tool of geometry called a protractor. And you guys have probably seen one of those before. My smartboard tool has, this little guy right over here. So if you've used a protractor before, here's what you'll hopefully remember. You want to take this little center point on the bottom of your protractor here and put it right on the vertex of your angle. So probably something just like that. Then what you want to do is rotate that protractor a little bit so that the bottom line of the protractor is directly on. I'm not sure how this works right here, guys. Can I click on this thing? It's directly on. No, that didn't work. And I don't think that worked. I'm not sure how to work the protractor right here. Well, that didn't work so well. Hang on a second. Can I double click? No. I have no idea how that works on here. Anyway, you'd kind of spin the protractor and read the numbers on the outside right there, and you can figure out how big that angle is. We'll get to that a little bit later, but I do want to make sure that everybody understands these 3 concepts right over here. They're going to be important with everything that we do to measure angles. Most of you guys know this already. One full circle, guys, if you were to start here and go all the way around something like that, is going to equal 360 degrees. Now, that was a man-made choice right there, that system, and it comes from the fact that back in the day, many hundreds, if not thousands of years ago, people used to think that it took 360 days for the Earth to orbit around the sun. So if you think about cutting up a pizza, you can cut it up into as many slices as you want. Early astronomers decided to cut this diagram up into 360 very small slices right here, each one representing how far the Earth would move in one day. So they were wrong. We now know that it takes a little more than 365 days for the Earth to go all the way around the sun, but this was the system that they believed in at the time, so they decided to cut our big pizza up, our circle up, into 360 degrees. Probably didn't know where that one came from. Now you do. Half a circle then, like I have drawn in this protractor right over here then, is going to be 180 degrees. And guys, that amount right there there. Put a little star by that. The fact that a half circle is 180 degrees is one of the most important ideas we're going to use in all of geometry. We're going to come back to this number over and over and over again, so we want to make sure we understand that. The quarter of a circle, which inadvertently I almost drew right here and here then, 1/4 of a 360-degree circle is going to get us 90 degrees. And some of you know the significance of that. We'll talk about that in just a second. So let's make sure that we understand these three quantities right over here. Those are things we should have memorized. And even out there in the real world, when you're dealing with people that aren't in a high school geometry class and maybe don't know a whole lot about math, this is something people are going to expect you to know. A complete circle is 360, half of that is a 180, and a right angle, oops, gave it away, is going to be 90. Speaking of which, let's talk about some angle classifications. And again, these are things you guys probably learned in middle school. Let's hit them again. An acute angle is one whose measure is going to be less than 90 degrees there. Technically, it has to be more than 0, but most people leave that one out. So a drawing of an acute angle here, guys, there's one ray, and now a second ray coming from the same endpoint right there, and it might look something like this. So an acute angle is pretty sharp, pretty pointy right there. You can kind of think of it that way. A right angle is another one that most people know. A right angle has a measure that is exactly 90 degrees, and not close to, exactly. So not 89, not 91, not 89.9. It has to be exactly 90 degrees. And as you look around you guys, unless you happen to be out in the woods right now, if you're inside a building, you probably see right angles all around you in terms of the floor, the ceiling, the walls, how things intersect. Almost everything we build in the world is made up of right angles because they stack very, very nicely. So a right angle would have one ray like this and maybe another ray like this. And there's a little symbol that we use in geometry to indicate that something is a right angle. You don't just want to assume. And it's this little box here that we put in the vertex of an angle, and that's called a corner mark. All right. With other angles, like this acute angle above, we put that kind of circular tick mark or arc mark right there. But if we want to specifically denote that an angle is a right angle, exactly 90 degrees, we put that little box in the corner there. Okay, an obtuse angle, everybody. I'm going to be a little specific with this one right here and say that the definition of an obtuse angle is between 90 degrees and 180 degrees. It's tempting just to say obtuse is bigger than 90, but by that definition, a 245 degree angle is obtuse, and that's really not correct. So an obtuse angle, I'll draw one ray pointing out here to the right, and now I just need to make sure that I open this thing wider than 90 degrees, so this would be an example of what an obtuse angle might look like. Now my guess would be you learned about acute, right, and obtuse angles in middle school, but you probably didn't learn about a straight angle. Well, if I asked you to guess, you might be able to come up with it, especially just from the definitions of the other three. Acutes are less than 90, rights are exactly 90, obtuse angles are between 90 and 180, and a straight angle here, guys, is exactly 180 degrees. So that is going to look a little funny because here's going to be my initial ray. I got it pointing straight out to the right. 180 degrees would take me all the way over here. There's the half circle that we talked about before, and a straight angle is going to look something like this. And that is now the second time in these notes here that we've talked about a diagram like that. What we're really dealing with a straight angle here are opposite rays, which we discussed earlier, and opposite rays are really the same thing as a line. So these three phrases, straight angle, opposite rays, and a line, they're really all the same thing. The point is that's exactly 180 degrees. Okay, so that's how we classify angles now, and we've got a little bit more vocab to knock out before we start solving some problems. If you learned this word correctly here in Chapter 1, congruent, then you should know how it applies here to angles. Congruent angles are angles with equal measures. We generically define the word congruent as having equal measures, so it means the same thing here. So if I were to draw an angle here that looks a little something like that, And I'm just going to guess here, guys. That's definitely an acute, it looks like an acute angle. I'm going to say that this one is about 50 degrees right over here. If I now wanted to draw a second angle, it doesn't have to be pointing the same direction or anything like that. If I drew another angle right here that was also 50 degrees, we could make our statement here that, let me call this angle Y, and this one right here, angle Z. We could say that angle Y is congruent to angle Z. That's the way we would write that. And the reason why, look at your definition, congruent angles have equal measures. Well, sure enough, 50 and 50 are the same. Now, even if we didn't know what those measures were, there's another way we can indicate here that the angles are congruent, and that would be with those circular tick marks that I talked about before. Just like tick marks with line segments back in section 1.3, as long as you have the same number of tick marks in two angles, that indicates they're congruent. So right now I've got 1 and 1, so I could conclude that those two angles are congruent. Or I could put a second arc mark here on angle Y, and then a second arc mark there on angle Z, and that indicates that they're congruent as well. Even if they don't really look like it, guys. Obviously, I freehanded this diagram right here and just drew it by hand, so there's really no guarantee that I've got those right. And I wonder what would happen now if I move this guy over and spun it a little bit. I guess we'll find out how close I was. Not perfect. Okay, I was just trying to guess there and get it relatively close. But the point here is that with those red tick marks, even if you did a lousy job of drawing them, you have to say, okay, those angles are congruent because the tick marks tell me so. So that's how congruent applies to angles. How about an angle bisector? Now again, bisector is a word we learned in chapter 1. We learned it in a line segment here. We talked about a midpoint bisecting a segment. Now we see it in the context of angles. The word bisect, let's break it down. The prefix bi means two, and sect means a part of something bigger. So to bisect something means to cut it into two equal or congruent parts. So here we go. An angle bisector is a ray or a segment that divides an angle into two congruent parts. So this red ray that I've drawn with the dotted line right here, I tried to draw that so that it split that bigger black angle right down the middle. Now, if I wanted to indicate that, I would need tick marks right here on the first angle, and then the same number of tick marks right there on the second angle. And those blue arc marks now indicate that these two smaller angles are congruent, and therefore we know that what we have there in red is in fact an angle bisector of the larger angle. Okay, so that's what an angle bisector looks like. Okay, a little more vocab here. Adjacent angles. Now that word adjacent, you might have heard in other contexts outside of a math class. Like for example, Illinois and Wisconsin are two adjacent states. They butt up right next to each other and they share a border. So when we're talking about angles, this definition's a little wordy, adjacent angles are two angles that lie in the same plane, have a common vertex and one common side, but no common interior points. That's a lot. All right, here's what it looks like. I'm actually going to go back to a diagram that I drew earlier. I'm going to draw kind of a large angle like this, okay? And I'm going to call that, you'll see why in a second, this point A and this point C, and this one over here, I'm going to call that one point Z right now. So I've only got one angle, but now I'm going to draw another ray kind of shooting down the interior of that angle, and I'm going to call that point right there B. Now, quick question I would want to ask you guys, how many angles did we just draw within that diagram? A lot of people want to say two. They said, here's one angle and here's a second angle, but there's a third angle that's the big, larger overlap right over there as well. So there's actually three angles right here. And if we wanted to name adjacent angles, we'd have to pay attention to this definition and look for two angles that lie in the same plane, which they all do, have a common vertex, well, that's going to be Z for all of them, and have one common side. Now, ray ZB is going to be that common side between which two angles? The one on the top, guys, angle AZB. Let me write that over here. Angle AZB. And there's another angle now that shares that red ray and has the same vertex. That'd be angle BZ and C. So angle BZC. Those two angles there are adjacent angles. They're right next to each other. They share the same vertex. They have the same side. They both share ray ZB, but no common interior points. Like, for example, point Q right here is in the interior of angle AZB, but it's not in the interior of angle BZC. So this statement is one you guys should put in your notes right there. That's what it looks like. Now, a little bit of a warning right here. What do you guys think about, let me name the same angle first here, AZB and angle, all right, see if you can follow me here, AZC. So AZB is this angle here on top that we were just talking about. That's this one. But AZC is this larger angle right here. So are these two angles here adjacent? Let's go back to our definition. Do those two angles lie in the same plane? Yes, they do. Do they have a common vertex? I can tell that from the names, guys. Yeah, they both have a vertex at point Z. So yes. Do they share a common side? I can tell that from the name as well. They both have ray ZA, which is this ray right here, guys, as one of their sides. But where this one falls apart is right here. No common interior points. Let's take a look at point Q again, everybody. And Q is inside. It's in the interior of angle AZB, but Q is also in the interior of AZC. So the answer to this question right here is no, these two angles right here are not adjacent because they overlap. That's the simple reason there, guys. But AZB and BZC, those angles don't overlap, so they are adjacent. Okay, almost done with the vocab right here, guys. Next one, linear pair. Now you can kind of figure this out from the name. Linear starts with the word line. Pair means two. So a linear pair is a pair of adjacent angles with non-common sides that are opposite rays. Ooh, I'm going to start drawing that. Opposite rays. So here's kind of a starting point in the middle, and I'm going to draw one ray going straight out to the right. Its only opposite ray would go straight out to the left. And now I'm just going to draw a random ray kind of sticking up from that point. And in doing that, I formed one angle here on the left and a second angle here on the right. And what I've just drawn are two adjacent angles, same vertex, they share a side, they share a vertex, I said, but they don't overlap at all. And they're non-common sides, which would be this one here and this one here, are opposite rays. So in a linear pair, we basically have a straight line down there on the bottom, and we've cut it up into two angles. So make sure you have that diagram in your notes. And now, one really important comment right here, guys. Angles that form a linear pair must add up to, let's think about that now, how many degrees? So with angle 1 and angle 2, if I kind of draw one big swoosh mark that covers both of those, what I'm hoping you guys notice is that this is a straight line down here on the bottom, and it kind of looks like I drew a half circle right up there on the top. And if we go back a couple of slides, maybe we'll remember, guys, that a half circle right here is 180 degrees. So back to this one right here, angles that form a linear pair must add up to 180 degrees. That again is a really important concept as we move forward. So we want to make sure that we have that in our notes and that we have it correct. Last definition right here before we dive into some examples, and this is probably new for you guys, vertical angles. Two non-adjacent angles formed by two intersecting lines. So I'm going to just kind of read this backwards, and I'm going to start by drawing two intersecting lines. So here's one line, arrows on both sides. Here's a second line here that intersects the first, and they cross right here at this one point of intersection. Now, when you do that, how many angles have we formed? Looks like we've got a grand total right there of 4. 1, 2, 3, and 4. Now, definitely, we've got some adjacent angles here within this diagram. Let me focus on angle 1 right now. Which angles are adjacent to angle 1? Sharing the same vertex, but right next to. Well, that would be 2 and 4 that are adjacent to angle 1. But for vertical angles, we wanted non-adjacent angles. So the only angle here that's not adjacent to angle 1 would be 3. They have the same vertex here, but they're non-adjacent, formed by the same two intersecting lines. So we would say that angle 1 and angle 3 are a pair of vertical angles. But likewise, the exact same rationale applies here to angle 2 and angle 4. So we could also say that angle 2 and angle 4 are a pair of vertical angles as well. But not 1 and 2, those are adjacent. Not 2 and 3, those are adjacent. And so on and so forth. And then, the big important takeaway from here, vertical angles must always be what? Well, let's do a little math here, guys, and let's see if we can kind of break this diagram down. If I were to just make up a number and tell you guys that angle 1 is about 80 degrees, and that's probably close, it looks like it's a little bit smaller than a right angle, we should be able to figure out the measure of angle 2 already. 1 and 2 are adjacent. They form a linear pair because there's a straight line here. And we just wrote down on the last slide that angles that form a linear pair have to add up to 180. So angle 1 and angle 2 have to make a total of 180 degrees. So we could take that total, 180, subtract the one angle that we know already, which is 80. I used nice simple numbers right here. And we'd end up with 100 degrees for the measure of angle 2. Now, though, let's keep going around the horn. If we wanted to find the measure of angle 3, let's focus on this straight line right here. And we'll notice that 2 and 3 also form a linear pair right here. Those two angles have to add up to 180 as well. So let's subtract the 100 that we know from 180, and this is funny, that gets us right back where we started again. So angle 3 would have to be 80 degrees. And you could do the exact same thing with angle 3 and angle 4. They form a linear pair. Do 180 minus this 80, and you'll get 100 degrees for the measure of angle 4. So now, let's take a look at the pair of vertical angles that we named a second ago. Angle 1, which is 80 degrees, and angle 3, which is also 80 degrees, the same measurement. So hopefully you guys know where this is going. Vertical angles must always be congruent. And you'll notice the same thing happens here with angle 2 and angle 4. 2 is 100 degrees, 4 is 100 degrees as well. And no matter what number I chose to start with here, we would always find that this little pattern holds. Okay, guys, I'm going to stop this video right now. We'll come back and we'll make a second one with 3 more examples kind of showing you how to tie all these concepts together and use them in action.